Hello everyone, welcome back. This is the review from last time about linear classifiers. So yeah, let's see, there was a review somewhere. So we learned about the linear perceptron already, and but that's that was introduced in the machine learning community from a maybe biological perspective. But linear classifiers are also an important problem in statistics in general, and of course, often the last layer in a deep neural network is a linear classifier with a sigmoidal transfer function, and but also as linear models without the nonlinearity before. They're quite useful, and particularly in applications where you're lucky if you find some structure in the data. So maybe I think I discussed this in opposite to the situation in OCR where there's clearly structure because we humans can distinguish the different digits. But in many, for example, applications in healthcare, the goal is to, for example, prove that a medication works at all. So this to really, and in the data in a clinical study or in the observed data, this might be not always easy to see when there are placebo effects and other things which might hide this effect. So the effect might be quite small. And we discussed generative models for classification, logistic regression, and classification via regression. And then also discussed a little bit some issues in healthcare, in medical informatics. The generative modeling approach is quite general and does not just apply to linear classifiers, but we will not dig too deep into the idea of generative models. It would be a lecture on its own almost, but the basic idea is to form a complete model. In our case, a probability for the classes. So if there are only two classes, it's just one number. And then have a model of the observed data, x tilde. So x tilde doesn't have the offset, given the classes. And here you can be quite creative on the right side. And we will cover the simplest case, which means that we assume that this can be modeled by a multivariate Gaussian distribution. Because then, if we have these two things, then we can apply Bayes' formula and get what we are typically interested in, which is the probability of the class given the observed data. And this part here on the bottom simply can be expanded in this equation, and this again only involves things we know we have modeled. So this is the famous Bayes formula or Bayes theorem. This is so my example out of a long time ago, and I thought this was extremely cool. Maybe I can convince you also that this is interesting. So here we have so just one number, brightness of the wood, and here's birch, so it's a lighter wood. And but if the distribution of x, so of the brightness given birch, is pretty wide in this example, and here's the distribution for ashes. So these are two different kinds of wood. It is generally darker, but it also has some distribution. And you can start modeling this distribution over here. So then you get P of x given y, and maybe P of y, so there's the same amount of birchwood and ashwood. Otherwise, you can put in different numbers. If they have the same probability, just put in 1/2. And you apply this formula, and then you get the posterior probabilities. So this would be the one for ashes. And you see, even on the left side, it's the probability that ashes has this lightness is pretty small, but it's so much bigger than the probability that birches has this brightness. So if you do the normalization, the ashes wins by far, although this wood is relatively rare, or this brightness value is relatively rare. If it has this brightness value, it is pretty clear that it's ashes. And then somewhere there's a cutover point where both have the same probability. So if they would have the same prior probability, then this should be more on this side. Maybe here I should look at the example again. They assumed that one kind of wood is more common. So this is the cutover point. And over here the birches win. And then you can you have a lot of information. You can do anything you want. You can say, okay, this is the this is the decision point. So on the left side I say ashes, on the right side I say birches, or maybe a misclassification error of one kind is more severe than the other. Then you might put your decision, or there some sort of decision module further to the left or to the right. So you have this information and you can do with it what you want. So then we went to the example of the multivariate Gaussian, and it's written like this. So it's interesting evaluating it at x tilde, and it has a mean and a covariance, and the covariance is shared between the two classes, but they have different means. So this is a prefactor here, then there's exponent minus 1/2, and then you have the expression xi minus the mu of that class, L is the class 1 or 0. So this is a column vector, but then you put the transpose, it becomes a row vector. Then here's the inverse of this covariance matrix, and here's the same vector again as a column vector. And if you multiply this by this matrix and this row vector, you get a number out, and this is then the probability density for this x given the parameters. So this is how a two-dimensional Gaussian looks like. And the estimates are quite obvious. The one is the empirical mean of all the data points belonging to the corresponding class. And the covariance, since we have two cases, we have two means, so we take the corresponding data point with the corresponding mean, so either class 1 or 0, and essentially calculate what you see over here is called the empirical covariance matrix if you divide it by n, but we divide by n minus m, where m is the number of inputs, to get a so-called unbiased estimate. So it turns out to be more robust than the maximum likelihood estimate, which would be n1 over n over here. So these are maybe formulas to remember. They can also be derived relatively easy, but in particular the maximum likelihood estimate for sigma hat involves the derivation considering the determinants and the square root, and so it's a little tricky, but it's not terribly difficult. And then we can expand these terms, and we can write the final equation. So for example, the probability that class 1 is true given x can be written as a sigmoidal function with an offset or bias plus a linear term. And the linear term can be calculated in this form. So it depends on the mean of the two distributions of the two Gaussians, and then multiplied by the inverse of the covariance matrix. And as we discuss later on, it's important that the kappas, or the kappa where the class proportions do not appear in this equation. So that's good if we need to work with non-natural distributions here of the classes. This expression will not change. And this is the expression for W0, which is sensitive to the class proportions, of course. Yeah, and then we have special cases, which are the naive Bayes classifiers for the Gaussian, where in the extreme case we assume every dimension has is independently Gaussian distributed, but they all have the same sigma square. And then we also get a linear sigmoidal classifier when we decide on the class boundaries. And another important naive Bayes classifier is the Bernoulli distribution, where so this applies for binary features. So here the word is present or word is not present, and there's some other variants on this too. And also this can be written as a sigmoidal function. So from this generative approach, this Bayesian approach, with Gaussian distributions, we get a sigmoid out. And then we said, okay, maybe sigmoid is a good thing in general. And we applied, we calculated the likelihood functions and the cost function to be optimized when we use a sigmoidal output function with the interpretation of these probabilities. And yeah, I like this, personally I like this derivation best. So we just start with the Bernoulli distribution of y, so the class label and the probability that this one is theta, and that it's 0 is 1 minus theta. So this is called a Bernoulli distribution. I mean, it's the most simple distribution you can think of. And then in the, to change this into a member of the exponential family of distributions, which is also a big theory in statistics, you simply substitute the theta with a sigma of eta, because theta has this constraint and sigma now is unconstrained, and there's a theory behind it which I'm not telling you about. But then we have an easier model, no? So the probabilities are now sigmoids of eta, and now we can substitute eta by a linear function, and then we get what is called a generalized linear model. There's also a whole family of these models. This is the simplest one, and what we expected, maybe the probability that class 1 is true given x is simply the sigmoid applied to this linear function. So logistic regression is the generalized linear model for the Bernoulli likelihood model. And yeah, so there's a big theory behind these models. And in particular here in Munich, I think they have a long tradition in studying these generalized linear models. Yeah. You can also, if you do the multi-class version, you get the softmax cost function out. So I want to skip this. Then you can do classification via regression. And it's quite popular in cases where the input, I mean, there's a small influence of the input on the output, or there's a lot of noise on the data, and you're happy to find any structure at all, then linear regression is applied even in classification problems, in particular in medicine. Yeah, then finally we discussed logistic regression in medical statistics. So the important thing is that you, the input x1 is the important one. So the fact you're interested in, so in epidemiology might be smoking, environmental factors, and so on. Then you have the offset again, and you have other inputs. And the other inputs are so-called confounders or additional inputs. A confounder is some variable which depends where the decision or the environmental factor depended on and the outcome depends on. So there's this example, the famous example from Fisher, who thought there was a genetic factor which makes you want to smoke and also affects your likelihood of getting lung cancer. It turned out mostly not to be true. I think there was a small effect people found eventually. But then the genetic factor would be the confounder. And the solution would be, if you're aware, if you can measure the confounder, to add it as an input to the model. If you cannot directly measure the confounders, there are also a few things you can do, but that's pretty advanced and pretty tricky to apply. Or in treatment evaluation, X1 would be the medication or the treatment, and other inputs might be sex, gender, age, whatever. So in medical statistics, people define the odds and then the log odds. And the interesting thing is, if you look at the log odds ratio, it is exactly W1. So you have to plug in all these formulas. And so that's why the log odds ratio is quite popular in analyzing of medical data, because we also know that W1 is quite insensitive to a change in the class probability. So you don't have to take the data from a natural distribution, but you can select, let's say, 1,000 patients with the disease and 1,000 patients without the disease, which is not, I mean, you have to be careful. I mean, normally you have to take the data from the natural distribution, but if you do that and evaluate the logistic regression model and then look at W1, it is invariant to this to change of these probabilities. So that's why it's quite popular in medical analysis. Yeah. Okay, I think that was it. So if you're interested in, there's a appendix on information theory, maybe more for me than for you guys, but maybe one of you is, a few of you are interested in getting a glimpse on that. Okay, thank you very much.